So everyone, we're here today to talk about graph thinking. My name is Ryan Boyd. I'm on the developer relations team here at Neo4j. And I've spent a long time working with databases of a variety of forms. So I started off my career working with relational databases and things like MySQL and Oracle, and then spent a while at Google working on things like Google BigQuery, which is more of a columnar database. And now I'm here at Neo4j working on a graph database. And I'm working on a graph database because I believe that the world is connected, that relationships are important, that the patterns established with those relationships are important. So we don't need to just look at the discrete bits of data, but we need to look about how the data is connected. So I'm going to take a couple stories here first before I begin the official slides per se, and stories that I think are really interesting to me personally. And I'm going to switch over to my browser here and confirm with Corey that things are good. All right. So let's talk quickly about the Panama Papers. The Panama Papers is a leak that came out of a company called Mosaic Fonseca in Panama. It is a database of tons of connections between basically companies who are have offshore accounts in Panama and elsewhere, and the officers of those companies and the addresses and things like that. And so I'd encourage you all to check this out, and see how these relationships form, how these connections form in the real world, outside of maybe like the traditional social network world that people think of oftentimes for graph databases. So I use Docker to start the Panama Papers database up. The Panama Papers database is distributed by the ICIJ, or International Consortium of Investigative Journalists. And I use Docker, and it just said Docker run and RAG-IRG Panama Papers. You can find that in our blog post. But and it actually guides you through this data really nicely. They just launched a new form of this guide with a lot more details. I think that was yesterday that they launched it. But I'm going to show you how some of these connections are involved, and why the real world is actually about graph thinking. So in this case here, we are running this query that's the shortest path between two people. We're looking for officers of corporations which have offshore bank accounts, and the officers have the name Smith or the name Grant. And you can see here, this is how the world is related. So this is essentially finance data, and we have you might not be able to read all of this, so let me just introduce this to you here. We have Grant, someone with the last name of Grant, and we have someone with the last name of Smith, and we have someone with a first name of Grant here. These three purple nodes are people. And these people are officers of corporations. And they're officers of corporations that are highlighted here in red. Each of these people have addresses, which are in green. And you can see basically the path that you would travel to get from, say, this gentleman named Ian Stewart Grant to this other gentleman named Stewart something Smith, Onslaught Smith. The path that you would take to get between these two people is basically through their intermediary companies. And I showed a little bit kind of dense version of this graph. So hard to trace the pattern exactly with everything I've shown here, but you can see clearly that the world is really a graph here. We have people. Those people work for organizations. Those organizations have other entities related to them. Those organizations have addresses. The organizations are located in a particular place, in this case, Virgin Islands. And you can see how all of these things interrelate. And this is really representing the real world. And this is a much more valuable way to look at the data than looking at a table of addresses of companies. So that's why the data journalists chose to use a graph database. They had over 400 journalists around the world looking at this. And so the other example that I want to point out does go to the traditional social network world, but again is talking about a larger issue. So this is a analysis of the Brexit campaign by a gentleman named John Swain. And this is basically looking at the Twitter activity on related to Brexit. So people that are in communities in the Leave camp or in communities in the Remain camp, and this analysis was done a while ago before the decision was made. But you can basically see, and this is a really good example, when you look at the connections between all of these different people, and the volume of their communication. You can see, for instance, here it's very dense around the Leave side with a lot of noise. There's a question that John has here as to whether it's effective communication. Again, this was before the results came in, but you can see how dense it is, how all of these people in this community that are interested in having Britain leave the European Union are all communicating very much between each other. And then you can see the Remain side. Again, there is a lot of communication, but it's not quite as dense. So we're going to be doing similar sort of analyses for the U.S. presidential election, working with Neo4j, with Right Relevance and John Swain to do these sort of analyses on hundreds of millions of tweets and about the election. And so I look forward to seeing what this is. But the real world is basically determined by how these connections are made up and the strength of these connections, and not just on social media, obviously, but in real life. So let me hop back to the formal presentation and talk about, I said about hundreds of millions of tweets, but how much data do you really need for your business or for your use case? Well, there's one opinion on this. Tim O'Reilly says the person with the most data wins. I would argue that he's partially correct there. The person with the most data that knows how to use it effectively wins. So what type of data do you need, and what do you need to do to use it effectively? Well, relationship data becomes really important here. Having the discrete bits of data without understanding the connections between the data is quite not nearly as valuable as truly analyzing those connections. So the close relationships determine whether that data is relevant, and then the number of relationships increases the importance of that data. So you can see, if you remember that Brexit graph that I showed you earlier, there was a lot of very close relationships on the Leave side, and there was a number of relationships. There was an increase in importance because each of the nodes were communicating a lot with the other nodes. But if we step back to not just kind of how people in this world or companies in this world interact with each other, and we think about the human body, we have in our human body, we have 100 billion neurons and 100 plus trillion synaptic connections. We as humans are actually made up as a graph. We have the connections between each of our neurons comes in and looks something like this. We have a graph of nodes and relationships, or neurons and these synaptic connections. And that's how the human body is made up. And we definitely believe that the rest of the world is made up that way as well. And understanding how those connections are made is really important. The internet is another example of this. I saw, I think it was yesterday, it was Tim Berners-Lee. It was like an anniversary of the internet or something along those lines. And there was an article about Tim Berners-Lee where they said, yeah, right, that the internet is really going to take off. Well, obviously that has been proven wrong. But the internet is taken off or has taken off largely because of enabling all of these connections between people and businesses. And this has been really important for our generations. But it steps even to other examples. This is the genetic ancestry of a single corn variety. This is showing how the DNA of corn kind of traces back to different genetic components. And so the world is interconnected. Hopefully, I've convinced you that by now with some consumer examples and some examples from social networks and examples from businesses and how businesses are interrelated. But let's talk about how the graph thinking has enabled companies to be built, enabled companies to be better. Well, most successful companies in the world have taken data relationships and derived meaning and value from those. So Google has created perhaps the most valuable advertising system on the planet on top of their search engine. We see, the top one here is Monster, was the initial way of doing job listings based purely on search and not the connections between people. LinkedIn moved and now is focused on how people are connected. LinkedIn has built their own graph database for the main LinkedIn site in the United States, but actually recently we announced as LinkedIn China looked to implement their technology, they chose to use Neo4j as the graph database to connect people in LinkedIn China. Google is not using Neo4j yet, but we can hope. We also see how the traditional banks have been taken over by things like PayPal and Venmo, or these services have popularized money transfers and made it a lot easier for people to build those connections between individuals. So a lot of very popular companies have taken graph thinking and applied it to their business. So let's talk about what a graph is. A graph is a way of representing data. We have bits of data, and we have to talk about how that data relates. In a typical relational database, that data is separated off into rows and columns. And this is kind of good for understanding the structures of the data. You have a very hardly enforced schema, which says here are the columns, here are the types for those columns, and every row has those columns and those types. So it creates this well understood data structure. And as long as that doesn't change too frequently, that's fine. But there are problems dealing with the connectivity. So it works well for discrete parts of data, but ironically, relational databases don't handle relationships fairly well. They handle relationships with joins, and joins can be very expensive due to index lookups necessitated on each join. Companies and developers that are doing 15, 20, 30, 40 different joins in their queries have very slow performance characteristics, especially as the size of that data grows. So then we think about a graph, and you think about how data is represented in a graph. It's very similar to all the things that you have just seen. We have the nodes and we have the relationships between the nodes. It's very good when there's dynamic relationships, when it's hard to figure out in advance what the topology is. And the topology may not be, say, a strict tree structure, but a lot of interrelated connections that you don't know about in advance. And it is very good for when your requirements evolve and allows the graph to evolve and the data to evolve with your business. And then, it's also good for when Relationships in the data contribute the meaning and value, and not just the discrete bits of data. So not necessarily as good for log type data or something like that, but most types of data that you would rely upon a relational database for, where you have a lot of join statements in your queries, fit very well in a graph model. So Neo4j uses what is called the property graph data model. So a property graph data model is something like this. So we have our graph, and we have the relationships between each of the nodes in our graph. And these nodes could represent something like lights, or the road here, or traffic. So a road has lights on it, a road has traffic on it. And here's an example of a hotel, a different graph. A hotel has rooms. Those rooms have availability. And you could think of like different properties that might be on these relationships. So a hotel has rooms. Rooms can have properties. What size bed are in the rooms? A hotel can have properties. Where is the hotel located? Or how many stars has that hotel received, and things like that. Those properties can all be stored on those nodes. And then also on the relationships, you can store properties as well. So on this has relationship, or on the available relationship, different properties can be represented on those relationships that further describe those relationships. So I like to think of the nodes as being the nouns, and the nouns have properties, which are adjectives that describe those nouns. And then we have the relationships are the verbs, and the relationships have properties which describe those verbs, which are the adverbs. So here's an example of showing a property on the relationship here, and a property on this node. So this is about how three people know each other. And we could say that the person down at the bottom here has a name of Anne. That's a property that's on her. And Anne knows this other person since 2012. So the since 2012 is a property that is on the relationship, the knows relationship. So again, we have our properties, we have our relationships, we have our nodes. And here's the sort of complete graph, but it's showing how we can add additional people to the graph as time changes. So as different people establish relationships with the data, we can just add them into the graph without any schema changes or things like that. And we can also add in additional types of properties and additional types of nodes and relationships on the fly as we learn more information. So in this case here, we originally had the nose graph with the three people in the triangle on the left. We added a new person in who knew one of the original people. And we decided we wanted to store information about what schools these people studied at. So we can add a node in for the school, Columbia in this case, and we can add a new relationship type, studied at, between these people. And we can do all of this on the fly without any sort of schema migrations. You can arbitrarily add new properties or new relationships as you need, as the business or use case demands. And you can see we keep on doing that as we expand our graph. We added our schools. We decided to add the schools for the other people. We added companies that the other people work for. And you can keep on expanding the graph to make it more and more interesting, to represent more and more information about how each of these people are connected amongst themselves and with institutions. If you think about that, as being one small part of the graph that your application is using. And then you think about how all of these other nodes are connected and what are the relationships and patterns that those connections form. This is what gives you your value, not just the small number of 10 nodes, but if you run those sort of relationships with each and every user in your system or entity within your system, you start to build a more interesting model that then you can derive value from. So let's talk about that, graph thinking in practice. Talk about the types of use cases which graph databases are used for. And I'm going to introduce these types of use cases, but I will say in advance that it's very broad. A lot of people initially think of graph databases as being primarily useful for social networks. And it's true that they are useful for social networks, but the world is a social network as humans and as companies and entities that we don't typically think of as a social network. And there are a lot of other use cases which Neo4j and graph databases can be super valuable for. And we're covering just some of them. Some of them are broad, some of them are more specific, but let's start by talking about real-time recommendations. So I say real time, and I'm saying real time because one of the things that has become problematic over time for companies that are trying to do product recommendations is the amount of data and the amount of customers and people has become so large that they're forced to do their recommendations in nightly batch jobs. They do these as offline jobs, analyzing this type of graph data, but without using a graph database to produce their recommendations. And the advantage of a graph database like Neo4j, where we are a native graph database, and that means that we're storing and traversing these connections as a graph. So in the case here, if we start from the left of this graph, we have a person who bought a flower pot and also viewed a watering bucket. Sorry, I don't even know what that's. Watering device widget. So the person bought something and they viewed something else, and then we can trace those connections for other people who bought the watering bucket widget. They viewed a pail maybe, and someone that viewed a pail viewed a wow, I'm not up to date on my gardening tools, but viewed a gardening tool or bought a gardening tool. So all of these relationships between what people bought and what people viewed and what other people who bought those items viewed, etc. You could traverse this whole graph. And folks used to do it in the batch jobs, but now because we can traverse this graph very efficiently in a graph database, because we're essentially just doing pointer arithmetic as we navigate between these different nodes, we can make these recommendations in real time, and we can stay up to date, and we can make sure that when we're recommending a product to someone, it's not a product that they've already purchased. I don't know how many of you have experienced this, but I've certainly experienced this big challenge where, I'm browsing a website and it keeps on giving me recommendations of things that I don't care about or that I've already purchased. And it's kind of frustrating. It's like, I wish they would recommend me more valuable products. My credit card probably doesn't, but I wish they did. And so that's kind of the scenario here, is that by using a native graph database, we enable these real-time connections. So we saw this retail graph with essentially two relationships: what items were bought and what items were viewed, and the people. In a real graph doing recommendations, because we're able to do this in real time and we're able to compute this quickly, we can add a lot more different types of data into our system. So you're not going to be able to see all of this, but I'll talk through it. We have a person who looks at or viewed a product. And we have how that product is related to all the other products. So that left part of the graph is actually representative of the types of things we just saw. But the bottom, top, and right part of this graph say we should really be taking into account additional things when we decide how we do our recommendations. We should take into account the person who is looking at a product, and we should understand what that person has complained about in the past in our help desk system or with our customer service reps. Did they complain about a KitchenAid blender? So no matter that the KitchenAid blender happens to be the most highly valuable product and the highly rated product, it turns out that they complained in the past either about a KitchenAid blender or maybe just about other KitchenAid products. We should take that into account and probably not recommend a KitchenAid blender. You can also take into account as you build your network full of things like tweets or emails or their reviews of other products. Look at the manufacturers of products that they reviewed highly or reviewed poorly. If you think about your inventory and you think about holidays or other special events, there might be cases where you think someone is shopping for a special event and you have the items in your inventory that are not going to be able to be delivered in time for that special event. Your logistics system tells you that. So if you integrate your recommendations with your logistics system, you can prioritize showing those items which will be delivered faster in time for that special event. And this continues and goes on based off of the activity of the user and their interactions with all of the different systems that you have. You can make much more better informed product recommendations or recommendations for other things like content. So we have folks like Walmart, leading companies, using us for product recommendations. But if you think about the same sort of things, like I was saying with content, these product recommendations, these ideas behind product recommendations can also be used to recommend content. And we have folks like the Financial Times using Neo4j to recommend content. So master data management. I personally view this as kind of an overloaded term. Within a company, the idea is that there's master data, and you want to see how this data relates to all the other data within the company. And oftentimes, it's thought of as how the employees relate to the customers and the products and the sales cycle and things like that. So that's what this is showing you here. And it's very clear that this is a graph. We have people who manage other people within our organization. Those people lead particular projects and collaborate with other employees on those projects. They may represent certain regions from a sales territory perspective. And you can see that all of this is really relationships that are built on the fly as the business changes. We have leading companies like Cisco using us to determine how things are, whether things are appropriately governed within their organization, and having this one single source of truth for the hierarchies that Cisco has. And this actually reminds me we've shown some things which take advantage of graph analytics, looking at clusters, looking at relationships, patterns from an analytical perspective earlier in this presentation. But Neo4j is really an ACID compliant transactional database. It's meant to be the source of truth for your data as Cisco uses it for. Fraud detection. It's a very popular use case for Neo4j. We have a lot of financial institutions and even online gaming companies and other things using us for fraud detection. This is one of those areas where we don't have many public references because people don't like revealing the technologies that they're using for fraud detection, but it is a very popular use case for Neo4j. So you can see here in this example graph, we have a person who has opened an account with a bank. That person has been issued a credit card. The person lives in a house. And you can see their relationships with other people and those credit cards and where they live, and potentially with things like social security numbers and telephone numbers, and the patterns that you start to discern from the relationships between all of these entities can help you uncover fraud. And so we have a cybersecurity expert, Gorka Sadowski, who said that graph databases offer new methods of uncovering fraud rings and other sophisticated scams with a higher level of accuracy, and are capable of stopping advanced fraud scenarios in real time. Typical fraud detection uses a very discrete analysis approach. Is this pattern of activity outside or an outlier compared to what is known to be good activity? But by looking at the connections between all of these different entities, we can stop more advanced fraud schemes. Graph-based search is actually one of the original use cases for Neo4j. When the founders created Neo4j, they were looking at a library of media, a library of photographs, and trying to figure out how you describe and search photographs effectively. And so they found that there were things like, let's say you had within your database of photographs, you had dogs, pictures of dogs. Well, understanding that when someone searches for the word animal, they should find both things that were tagged with animal, but also things that were tagged with related tags like a dog. And that's actually an important thing. If you look at kind of how all of these terms interrelate, it helps you find better content. And so in this case here, you're seeing on how a photograph was captured and published and how it was included in particular publications. And you think about all of that graph and you can use that to better find new assets. And this also aligns well with the content recommendation stuff that I talked about earlier, where folks like the Financial Times are using how the entities mentioned in a news article interrelate to each other and allow you to then browse other related news articles based off of those entities. And Lufthansa is also using us to manage the digital assets in its new version of its in-flight entertainment system. Network and IT operations. A network is a classic graph. Graph and network are often used synonymously in industry and in computer science. And a computer network is a graph. So we have machines that are connected to switches that are connected to routers that are connected to gateways. We have on those machines may be hosting particular services. Those services are dependent upon each other. So in this case here, we have a database, and we have applications that are dependent upon that database. And that database also is dependent itself on having power. And the power comes from our UPS systems or similar. So you can see all of these things are interrelated as a graph. And what value does it add by thinking about it as a graph? Well, it allows you to do dependency analysis. It allows you to say, hey, I'm going to be taking down this rack. And who are all the end users that are actually going to be affected by taking this down? And I want to contact them in advance and let them know that I am taking down this rack so that their application X, Y, or Z is not going to be available for the next few hours. Similarly, you could actually use it for root cause analysis. You're noticing a bunch of applications have failed to respond, but you don't understand exactly what's going on in your infrastructure yet. You can understand more by looking at all the commonalities between those applications which are experiencing issues. So this is something that you want to check out probably if you're in the network and IT operations space. There's a thing called MacGyver. which is developed by the folks at Lending Club, and MacGyver is an open source project which manages microservices and all of their dependencies for their IT infrastructure at Lending Club, but you can also use the MacGyver software yourself in order to manage your own infrastructure. And we have leading folks in the network world using us, such as HP, and then also major telecom providers. Think of things like Orange in Europe. Identity and access management, another case where the world is a graph. Oftentimes with identity and access management, companies try to represent this in a tree-based structure. So if you think of a technology like LDAP, years ago, I worked for a university, and we had LDAP infrastructure with three main OUs: students, faculty, and staff. And people had to belong strictly in one of those categories. They were either a student, or they were a faculty member, or they were a staff member. And as you might imagine at a university, there's often a lot of overlap between these different constituencies. So you'll have students that also teach classes. You'll have staff members that take classes or teach classes as well. And so people belong in multiple places in this tree hierarchy, but a tree doesn't allow you to really represent that. So we ended up creating fake accounts, and people would have to log in using different accounts for their different roles. And this becomes really painful. We have other folks that have, as customers, we have folks that have very, very dense graphs of the relationships between their various permissions on their systems. So they'll have a user that's within a group, 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 etc. And it's such a deep hierarchy or graph of the relationships between the users and these access control groups that they have to calculate these the user's permissions for individual applications in a batch process in advance. They can't do it in real time because it just takes too long. If you have to go log into your application, it takes 5 minutes because it's looking up all of your groups and the subsequent permissions. That's going to turn you off. So they do it in batch. And when they hired someone new to a group, or when they let go of someone, it was just very difficult to get them deprovisioned right away or provisioned right away. So they moved into using Neo4j and storing it as a graph, and it allows them to do these analyses in real time. It allows them to figure out when a person's trying to log into an application, what permissions does that person have to that application. So we have major finance companies, in this case UBS, that use Neo4j for things other than fraud detection, and they're using us for identity and access management to manage the permissions amongst all these assets. So you've seen throughout each of these different use cases how a graph thinking applies, how the relationships between the different bits of data add more information to your business and enable you to solve problems which you couldn't solve before, or which you had to resort to batch overnight jobs and such to resolve. So why graph thinking? Graph thinking because it is intuitive. The intuitiveness of a graph is there because it represents the real world. The way that you look at the real world is as a graph. You think about people, and you think about who those people are related to. You think about cars and where they're coming from or going to. You think about all the different objects in the real world. In your mind, you're actually thinking about this as a graph in many cases. It also leads to performance. It leads to speed, and speed can come in multiple forms. Speed can come in the form of execution, enabling us to view these real-time, sub-second lookups in our graph database for things that previously had to be computed as batch jobs. But it's also about speed of development. It's about the intuitive nature of a graph allows us to build our applications a lot faster because we are not translating between what the computer thinks and what we think naturally in the world. The agility also enables speed as well. Agility is about the ability to adapt our model and grow our model as we proceed forward. So in the case of the graphs that you've seen here earlier today, you saw how we took our graph of people and how those people are related to each other, how they know each other, and we added in some additional elements. We added in the companies and we added in the universities, and all of that bit of data. That is showing the agility. We could decide that new information is important, and we can add that new information on the fly. So let me just give you a couple more examples of some of these properties of a graph database, and specifically around the intuitiveness. It's naturally how the world is represented. It's naturally how the world is represented because the whiteboard model is the physical model. What you draw up on the whiteboard is actually how the data is represented in the database. And that eliminates that translation between your business folks and your developers, and that makes it a lot faster to develop. I'll give you another example here with speed. Here's a quote from eBay. This is for their real-time delivery service. They found Neo4j to be thousands of times faster than their prior MySQL solution, with queries that require less code. So it's faster to develop and maintain, but it's also faster to execute. And this is actually really impressive in this particular case. They're basically, it's real-time deliveries. They have a product. They have people that pick up that product from a store and then deliver it to a customer. And they were actually finding their fastest delivery from a person going out to a store and picking it up and delivering it to a customer. Their fastest delivery was actually faster than their longest running MySQL query in order to calculate this route. And so, we were able to provide them with the speed and their customers with the speed that they never had before. So one of the reasons I talked about agility, it's the naturally adaptive model that we talked about, but it's also about a query language that's designed for connectedness. So, SQL is the standard query language when you're dealing with tables and columns and rows. Well, Neo4j has a thing called Cypher, which we've now opened up as Open Cypher. And Cypher is a query language that's optimized for graphs. And it's optimized for graphs because it deals with these relationships very well. So there's a SQL join statement here on the left that is basically a bunch of joins, and the data is unioned together. So this is trying to query people in an organization at various levels of the hierarchy, and they have union statements for each level of the hierarchy. Which is really painful to write and also not very performant. And the reason that they have this, it may be because it's not the world's most optimized SQL query, but it is a SQL query by a real customer that they were using prior to implementing Neo4j. And that same query using Cypher looks something like this. Find me a boss who manages a subordinate, and that subordinate manages other reports up to 3 degrees in each case, where the boss's name is John Doe. And then return the subordinate's name as well as how many total reports that subordinate has. So this allowed, with having Cypher, it allowed them to spend less time writing their queries, less time debugging their queries, and made for code that was much easier to read. Here's a simple Cypher statement. We have Anne who loves Dan, and the graph looks something like this with the two nodes, Anne and Dan, and the loves relationship between them. We can look for Anne loves Dan to find this exact match that we're familiar with, or we can say, let me find a person whose name is Anne with a loves relationship and another person whose name is Dan. So again, we have our nodes and our relationship. So then if we're trying to specifically look up whom does Anne love, we could say, find me the pattern of a person loving another person, and the first person's name is Anne, and return the whom. Return who loves who loves Anne. Whoops. Fast forwarded through that a little bit quickly, but we have users that love Cypher. A lot of people, when they first look at Cypher, it's not that familiar with them, but if you spend a few minutes or at least a few hours and review Cypher and try to match some of these patterns, it becomes very natural. It's thinking like a graph. It is about drawing patterns between the different entities and querying for those patterns. So graph thinking focuses on the relationships to turn data into information and uses the patterns to find meaning. It's all about relationships and patterns. So to learn more about this and about Neo4j, I would encourage you all to register for the Graph Connect conference in San Francisco. It's coming up this October 13th and 14th. We're currently working on the schedule of sessions, but we'll have something around 20 different full-length 45-minute sessions, mixing both business and technical topics, as well as a dozen lightning talks, shorter sessions that really just kind of whet your appetite on various topics. That's on October 13th, and then the 14th is a full training day, so you can get trained up on Neo4j and learn how to think more like a graph, how to model your data as a graph, and I believe we'll also have production training as well, so that you can learn how to run a Neo4j cluster. And you can register for that at graphconnect.com.